In this video, we're going to do a matched pairs T procedure. A boutique fitness studio would like to test whether their program is effective at weight loss. They randomly select 6 female participants to adhere to their diet and exercise regimen for 12 weeks. A before and after weight in pounds was recorded for each participant. Consider all conditions to be met. We want to use a significance level of 0.10, and we're going to assume that the population of differences is normally distributed. We want to use the following to answer the questions below. So we can see here that this is going to be dependent or paired data. Because we have one participant and then we have 2 measurements for that same participant. So for the first female, they had a before weight of 160.1 pounds and an after weight of 150.3 pounds. So this implies that these 2 measurements are dependent upon each other. And so the data is paired, which means that we need to do a matched pairs procedure. All right, so what is our main question of interest? It says, does the program promote weight loss? So what does this mean? It means that is the difference between the before and after weights in pounds greater than 0? So we need to take the differences and then use those differences to see whether or not the average difference is something different than 0. And more specifically, because we're looking to see whether or not there's weight loss, we want to know if it's greater than 0. So it's important that we take the differences, but we're not going to quite do that yet. If we want to continue on with our plan, we want to think about what the parameter of interest is. So what is the parameter in a matched pairs procedure? So the parameter we are interested in here is mu d. This is the true average difference in weight loss between the before the program and after the program. So the parameter is mu d, that's our unknown. And so our null and alternative hypotheses will be then concerning this parameter. So the null and alternative hypotheses will be h naught mu d is equal to 0. It's always a statement of equality, the null hypothesis, and the alternative hypothesis will reflect our question of interest. And because we want to know whether or not the program actually reduces weights, then if we take the difference between before and then subtract off after, if there is a difference, like if they lost weight, that means that these will be positive values. So what this means is that our alternative should be mu d is greater than 0, meaning we'll have positive values. And it's a one-sided test because we want to know whether or not it actually reduces the weight instead of just does it change the weight. So that's the difference here. That's why we're doing a upper one-sided test. Okay, according to our alternative hypothesis. All right, so now we need to start solving this. And so the first thing that we should do in solving is to take the differences. So take the difference between the before and after. So this first difference, 160.1 minus 158.3 is equal to 1.8. 154.4 minus 143.5 is 10.9. And so it doesn't matter which way you subtract. I always just suggest that you subtract it just like you would in elementary school, where you just subtract the lower or the thing on the bottom from the thing on the top. So just put like a minus sign here and subtract them. I think that that's easier to keep track. It's just important that whichever direction you choose to subtract, that's what you are consistent with throughout the problem. So I'm going to subtract after from before, like I've done for these few problems already. And we have 5.8 for participant 3. That's how much weight they've lost. 3.5 pounds for participant 4. 2.6 pounds for participant 5. And it looks like participant 6, unfortunately, actually gained 1.2 pounds. So the difference is a negative number. So 1.88.9 or 188.9 minus 190.1 is a negative 1.2. So now that we have our differences, we can then start making calculations and start solving this problem. So a matched pairs t-test is essentially just a one sample t-test on the differences. So once we take the differences, we can just treat that just like we would a regular data set. So if we want to solve for this, the first things we need to do is we need to check the conditions really quick. And we can just kind of do this verbally. If we look up here, we see that it says consider all conditions to be met. Well, that means that we had a random sample and that essentially the differences are normally distributed in the population, which we can see that, and we can see that the conditions are met, and we know that we have actually a randomly selected sample. So all the conditions are met for inference. Now, if we want to solve this, then we need to calculate d bar. So how can we do that? This is basically just the average of the differences up here. So we can calculate the average just like we did in any other circumstance. So we add up those values and divide by the total number of values. So in this example, it'll be 1.8 plus 10.9 plus 5.8 plus 3.5 plus 2.6 plus negative 1.2. All this divided by 6. So we get then, if we add all these values, we get a sum of 23.4, divide by 6, and we get an overall average weight loss of 3.9 pounds. So our d bar is equal to 3.9. Now we need to calculate the standard deviation of the differences. And we can do this using the same calculation we do for any standard deviation. Basically, this is the square root of di minus d bar squared all over n minus 1. So the number of differences minus 1. And so this is going to be equal to, scroll down a little bit, I'm going to start here. This will be equal to 1.8 minus 3.9. So each observation minus the mean squared plus the next observation 10.9 minus 3.9, the mean squared, plus the next observation, which is 5.8 minus the mean 3.9 squared, plus, and I'm going to carry this down here, plus 3.5 minus 3.9 squared plus 2.6 minus 3.9 squared plus the very last one, which is negative 1.2 minus 3.9 squared. So we take all those values, add them up, divide them by n minus 1, which in this case is 6 minus 1, and take the square root. So this is a little funky, but basically take the square root of the sum over these values. So what do we get from that? Well, we essentially get the square root, carry this along, of 1.8 minus 3.9 squared. It is actually just negative 2.1 squared, plus then 10.9 minus 3.9 is just 7. Square this value. 5.8 minus 3.9 gives us a value of 1.9. Square this value, plus negative 0.4. That is 3.5 minus 3.9, square this, plus negative 1.3 squared, and lastly, the very last value is negative 5.1 squared. All this divided by 5, and then we get, if we keep going along, if we square these values, we'll get 4.41 plus 49 plus 3.61 plus 0.16 plus 1.69 plus 26.01, all divided by 5. Take the square root of this. This is then equal to the square root of 84.88 divided by 5. This is equal to the square root of 16.976. And this is the variance, take the square root of it, and we finally will get the standard deviation of our differences, and that will be 4.12. All right, so now we have basically just D bar and SD. We haven't even calculated our t-test statistic yet. So this is why I really highly recommend that you use some sort of software to calculate your mean and your standard deviation, because it's pretty tedious. It's not impossible to do, it just takes a little bit of time. So once we calculate D bar, which again is equal to 3.9, and SD, which is equal to 4.12, we can calculate our t-test statistic to perform the hypothesis test. So t is equal to 3.9 minus mu d, which in this case is equal to 0, divided by our standard deviation of 4.12, all divided by the square root of the number of differences, which in this case is 6. So just to refresh you, this is t equal to d bar minus mu d, which is typically equal to 0, over SD over the square root of n. So that's what I've plugged into my t-test statistic here. And so I get a value for this of 3.9 minus 0 over 4.12 over the square root of 6. I get this to be equal to 2.32. This is my test statistic. So when I see this, then I'm going to look up my p-value, which it's from a t-distribution with degrees of freedom equal to n minus 1, and in this case, that's n, the number of differences is 6 minus 1, so this is equal to 5. So if I look up a t-distribution with 5 degrees of freedom, then I'm going to find the area. My p-value is going to represent that area that's above 2.32 in a t-distribution with 5 degrees of freedom. Now, I can find this from a t-table rather than using software or something like that. If we use software, then we'll get an exact p-value. If we use the table, then we'll get a range. And so let's go ahead and check out the t-table. Here's our t-table, and if we look at 5 degrees of freedom here and we scroll across this row, we can see that our test statistic of 2.32 falls between 2.015 and 2.571. We're doing a one-sided test because our alternative was one-sided, so that means we use a one-tailed p-value, so that means our p-value falls between 0.025 and 0.05. So our p-value is between 0.05 and 0.025, which means that we're going to reject the null because our p-value is smaller than 0.10, our significance level. So alpha was equal to 0.10. That means that we were going to reject the null based upon our p-value. Now the last thing we need to do is we need to calculate a 90% confidence interval so we can write up our 4-part conclusion. So the 90% CI for mu d, that's the unknown parameter, is equal to d bar plus or minus a t critical value times SD over the square root of the number of differences we have. So not the sample size, but the number of differences we have. And so d bar is equal to 3.9 again, plus or minus a t critical value. Let's go ahead and leave a little blank space for that for a second. We'll look that up on a t-table. And we have our standard deviation of our differences of 4.12. And to make this the standard error, we need to divide by the square root of our sample size, so 6. Now let's go ahead and find what t star is. Our t critical value comes from the number of degrees of freedom of n minus 1, so we've already established that that is 5. And so if we go back to our t table, we see that we have degrees of freedom of 5 here, and then we need to scroll down until we find the confidence level. Match up that column, so 90% confidence level. So that's the column that we're interested in. We need to match it with our 5 degrees of freedom. So it looks like our critical value is 2.015. 2.015. So if we plug that into our calculation for the confidence interval, we get 3.9 plus or minus a margin of error. So 2.015 times 4.12 divided by the square root of 6 will give us a margin of error of 3.389. So our 90% confidence interval for mu d is then equal to 0.511 pounds to 7.289 pounds. So let's go ahead and then finish our 4-part conclusion. So what this means is that there is moderately suggestive evidence the program helped to reduce weight on average, and the 90% confidence interval estimates the average difference in weight loss to be from 0.5 pounds to about 7.3 pounds. And I rounded a little bit here, with a best guess or estimate of 3.9 pounds lost on average. The null hypothesis is then rejected from a significance level of 0.10, where our t test statistic value was 2.32 with a p-value between 0.025 and 0.05 with degrees of freedom equal to 5. And that's how we can do a matched pairs t procedure.